project is consisted of a ground floor, typical floor first and second, and third floor. The main zones are the entrance lobby, the administration offices, outpatient clinics, patient's room, services, and the dentist clinic. U values for the wall construction, flat roof and double glazings were set as the building code for both London and Dubai locations. The dominant weather in Dubai is hot and humid. The rain is rare. The average temperature is 27 degrees, which is relatively high and above the comfort zone level. The dry bulb temperature in July and August is 40 degrees. The average wind speed is 5 meters per second. Dominated direction is northwest with an angle of 315 degrees. The proposed plot is located in Dubai Investment Park. The proposed plot has a dimension of 80 meters by 94 meters with a total plot area of 7,520 square meters. The plot is surrounded by a residential building and a park. The sun path diagram is plotted on the layout. The access to the plot is through two main roads as shown in the layout. In the building orientation strategy, 4 orientations were examined using the Flow Design software. Then the energy consumption for the 4 scenarios were then analyzed in the IES. It was found that scenario number 3 and 4 had the least energy consumption. Scenario 3 was selected as the flow design showed that the air is flowing into the building angle, creating a large positive pressure force. Strategy number 2 was about creation of vertical courtyards in the building facade. 2 different scenarios are examined in the second strategy. A void was created in the building facade to create a pull force. Green roof was added in scenario number 2. The wind velocity achieved in scenario 1 was 1.27 to 2.5 meters per second. The wind velocity achieved in scenario number 2 was 1.48 to 2.89 meters per second. Scenario 2 was selected as the optimum case. The third strategy implemented in this study was the cross ventilation. The wind velocity achieved in the base case was 0.02 to 0.04 meters per second. Scenario number 1 was adding windows of 2 meters by 2.9 meters in the building facade. The window velocity achieved in the first scenario was 0.02 to 0.08 meters per second. Scenario number 2 was enlarging the window size to 4 by 0.9 meters. The window velocity achieved in scenario number 2 was 0.03 to 0.09 meters per second. The scenario selected was scenario number 2. This graph shows a comparison between the base case energy consumption and the optimum scenario energy consumption. As we can see that the energy saving after applying the natural ventilation strategy is 0.96%.
The proposed site has a dimension of 80 meter by 94 meter with a total plot area of 6,000 square meter. The plot is located in Kingston High Street, which is surrounded by 3 main landmarks: Design Museum, Villa Complex, and a park. The access to the plot is through 2 main roads as highlighted in the below image. The sun path diagram is plotted to understand how the building interacts with the sun throughout the day. The prevailing wind direction is from the southwest side. London has a temperate oceanic climate, which is warm in summer and cool but not cold in winter. It has 1,600 hours of sunshine annually as an average. The large built-up area of London creates a microclimate, which is an urban heat island with heat stored by the city's buildings. Sometimes temperatures are 5 degrees Celsius warmer in the city than in the surrounding areas, according to the climate table created by London Weather Centre between 2001 and 2014. The average high temperature and the daily mean are the highest between June and September. 5th of June is the hottest day in London. The first strategy is changing the building orientation. The wind direction in UK is southwest. The flow design software was used to get the best building orientation in 4 scenarios. The energy consumption of the first best scenario was 12,440 megawatt per hour. The second best scenario was 12,436 megawatt per hour. The first option was selected as the best scenario. The base case at this analysis stage is the optimum option from the previous phase. Therefore, the courtyard location was selected to be facing the wind direction in order to enhance its impact. The idea is to add a vertical courtyard at the 3rd floor that will impact the indoor natural ventilation at the clinic rooms. Facing this courtyard, we examine the indoor spaces that will be affected by the courtyard in order to trace changes. The indoor temperature at the base case is recorded at 26.7 degrees Celsius and wind velocity at 0.04 meter per second. The cross sections are showing a poor velocity across the room. In order to create a courtyard while keeping the built-up area fixed, we moved the designated area 2 floors up, as shown in the 3D, and created a shaded courtyard at the 3rd floor and added a green surface where it can be utilized as an outdoor refreshing area linked to the clinic rooms. The indoor air temperature records a drop by 1.3 degrees Celsius to be 25.32 degrees Celsius, while the velocity increased to 0.06 meter per second. But the air distribution shown a high improvement as shown in the cross section since additional openings were added to the courtyard site. For further enhancement, we extended the green surface and re-evaluate the indoor spaces at the same conditions. This didn't impact the indoor environment since the air temperature was found to be 25.28 degrees Celsius and the wind velocity remains the same at 0.06 meter per second. Option 2 was found to be the optimum scenario for this strategy, where courtyard with extended green surface will be considered the base case for the next strategy. The second strategy aims to study the impact of window size and locations over the indoor natural ventilation, where the same spaces that were examined at the first strategy were the optimum scenario will be considered as base case for this strategy. The first option is adding another window of the same size at 0.9 meter height and 1.5 meter width, as shown in the isometric view, where the temperature dropped from 25.82 to 25.37. However, the wind velocity didn't change as it records 0.05 meter per second. But when we raised the same windows with the same size to be at 1.9 meter above floor level as shown in the isometric view. The air distribution is noted to be more unified over the indoor space, and the temperature is reduced to be 23.7 degrees Celsius. Since the solar gain is reduced due to the small window size, however, the velocity is still at the same range. At the third scenario, we enlarge the window to be 2 meter height and 1.5 meter width, starting from the floor level. The internal CFD analysis shows increase in air temperature compared to the previous scenario, as it records 24 degrees Celsius, while the air velocity is recorded at the same rate. Despite the fact that second scenario records the lowest air temperature, but since the analysis was carried on June and the aim is to raise the air temperature to eliminate the need for heating system during summer season, so the third scenario, where bigger windows is preferred to maximize the solar gain impact over the indoor environment condition. As a conclusion, the research proves that building orientation would definitely impact annual energy consumption, as it impacts the building envelope solar gain, which adds to the required energy to reach indoor comfort level. Therefore, it is recommended to test and examine different orientation for buildings in order to comply with each site requirements. On the other hand, it was concluded that adding shade courtyard will impact the indoor environment and natural air velocity at the interior spaces, especially when responding to wind direction and selecting courtyard location. On the other hand, window sizes and location of openings were found critical in terms of evaluating their efficiency, since the positive impact might be tested at summer months in London. For example, a negative impact might be recorded if the same design at the same location in winter. Therefore, full year analysis should be conducted to ensure eliminating negative impact, as well as other strategies shall be considered, such as insulation and material selection.